Okay, welcome everyone to the University of Birmingham Astronomy in the City virtual event for the 3rd of February 2021. Hopefully if you're watching live, you've already seen the first talk on what's in the sky this month. After this will be a Q&A session with researchers from the university where you will be able to come along and answer or ask us any astronomical or astrophysical questions that you might have, or maybe if you have a question about one of the talks you've seen this evening, then please do come along and ask us. We'd be happy to answer any questions that you might have. So my name's Dan Ryczanowski. I'm a third year PhD student at the University of Birmingham, and today I'm going to be talking about something which is very central to my PhD research, which is gravitational lensing. So gravitational lensing is a result of Einstein's general theory of relativity, and this is something that has really revolutionized our understanding of gravity and of the universe on a fundamental level in the past 100 years. It also has produced some of the best looking, in my opinion, images of the universe that we have ever taken, and in addition continues to be a corner of modern astronomy to this day. Okay, so first I'd like to talk about light. So light is something that, if left alone, will travel in a completely straight line. We can see a number of examples of this in our everyday lives. For example, shadows. The shadow that an object casts is a complete replica of the object that has cast the shadow. It has the exact same structure, and there's no changes there. There's no distortions. So from that we can deduce that the light must have travelled in a straight line to produce this, because otherwise the shadow would have looked different. You can also see light travelling in a straight line if you've ever been in a very dusty or smoky room. For example, in this picture of this abandoned theatre down here, you can see that the light rays are coming in, and because the light rays are bouncing off some of the molecules in the air, then you can see the light rays travelling in an exact straight line. You can also see this if you use a laser or a torch. Wherever you point the laser or the torch is exactly where the light will land. So these are just some everyday examples of showing that light normally travels in a straight line. However, in Einstein's general theory of relativity, this doesn't necessarily hold, because mass can bend the space-time around it, which causes the path of light to be deflected into curves rather than straight lines. So here's a diagram showing what this might look like. So there's a galaxy in the background. So remember that galaxies are made up of hundreds of billions of stars. So that's about 100 billion stars is roughly the amount of stars in our galaxy, the Milky Way. And the light from the galaxy is travelling on curved paths around this massive object. So this is a galaxy cluster here. You can see there's lots of blobs here. Galaxy clusters are the most massive gravitationally collapsed objects in the entire universe. So their mass makes them, excuse me, their mass makes them incredibly good gravitational lenses. And this light travels on a curved path to us here on Earth. So in fact, any object can distort the space-time around it in reality. So even me or you or this pen on my desk here, they can all distort the space-time around it and, in theory, cause gravitational lensing to occur. However, it's only really observable for objects with very large masses. So this is why we only ever see this in astrophysical contexts, where the lenses are things like stars or galaxies or clusters of galaxies, because these high masses really are needed to make this an observable effect. Another thing which is the case is the amount of bending that space-time the amount of bending that space-time feels is based on how close you are to that object. So if you're a light ray passing very close to the object, you're going to be bent a lot more than a light ray which is passing further away. So there are two things that influence how much light bends by gravity. One is the mass of the object which is doing the lensing, and two is how close you are to that object. So, so the idea of this came from Einstein in his general theory of relativity in 1915, and we're going to see here his first calculation, which was to do with the deflection angle of light coming from a distant star that passes near the sun. So in this diagram here, you can see that light from this star is coming along on this blue path. So if the sun wasn't here, it would continue going on in a straight line, and it would go down here and miss the Earth completely. Now, this doesn't happen because of gravitational lensing, so the path becomes bent slightly and travels towards the Earth and hits us. So for us, we perceive this star, or the light from this star, as coming from over here instead, because we always perceive light as coming from a straight line. So we see the position of the star over here, where actually it's coming from over here, or the actual position of the star here, but we perceive it as coming from over here because of the gravitational lensing. Astronomers like to work with angles, so we define this deflection angle here to tell us the difference between the actual position of the star and the apparent position of the star where we observe it, where we observe the light to be coming from. Now, it's actually a misconception that in Newton's theory of gravity, which predated Einstein's theory, that light is not affected by gravity. So this is a misconception, probably because light has no mass, and Newton said that gravity is an attraction of masses. However, in Newton's theory, you can actually calculate this deflection angle. However, there is one main difference between Newton and Einstein's theory, and that is the size that you would predict this deflection angle to be. If you take Einstein's theory, he predicts the deflection angle to be exactly 2 times larger than Newton's value. So, one way that you can decide whose theory was correct is to try and measure this deflection angle. And that is exactly what British astronomers in the 1900s set out to do. So the first successful measurement of this was done by Sir Arthur Eddington and Sir Frank Dyson. These two astronomers set out on an expedition to the island of Principe, which is just off the west coast of Africa, during the eclipse of the moon in front of the sun. So the reason the eclipse is important is because if you want to measure the position of these stars when the sun's there, you have to do it in daytime, and there's no way that you're going to be able to resolve the stars in the daytime unless the light from the sun is being blocked by something, in this case the moon. So if you look here, you can see the one of the photographic plate images that they took of the eclipsed sun. So the moon here is in front of the sun, blocking out the sunlight, so you can just make out some of the stars behind it. So you can see here, marked by these white lines, are some of the stars behind it. So this was a very fortuitous eclipse, because not only was it a total eclipse, so that the moon was completely covering the sun, but in the background was the Hyades star cluster in the Taurus constellation, which is actually the closest open star cluster to the solar system. So that means there was lots of very bright and well-known stars in the background for them to make their measurements. And actually, when they did the measurements, they found that the deflection angle did indeed match Einstein's theory as opposed to the old Newtonian theory of gravity. And this was huge news in the scientific community, because this was the first direct evidence that Einstein's theory of gravity was actually true, and that it matched up with what we see in reality. So after this point, Einstein's fame absolutely catapulted, and he became very quickly one of the most famous scientists in the world. So after the success of the 1919 expedition, no one really talked about gravitational lensing for about 20 years, until one man, Rudi Mandl, who was Czechoslovakian and working at the time as a restaurant dishwasher in the US, came up with some ideas to extend Einstein's theory of gravitational lensing using ideas of optics. So optics is the theory of the bending of light in glass lenses, as you'd have in a pair of glasses or a magnifying glass. He used some of those ideas and incorporated them into Einstein's theory in order to extend it even further. Obviously, the media absolutely loved this, because this is some guy who's just working as a dishwasher in a restaurant, and he's come up with some brilliant ideas to extend Einstein's theory. So the media absolutely loved that. But the ideas that he came up with included things like magnification, which basically is saying that the light from the gravitational lens, just like a normal glass lens, would focus onto the Earth and essentially increase the amount of light that we see from the background object. Now, this is something which is huge in modern astronomy because this means we can see objects that are further away because they've been magnified. We can see more light from them. And in fact, some of the most distant objects of the universe we've ever seen have been because of this idea of magnification from gravitational lensing. And another thing that he came up with was that it might be possible to see two images of the same object because of gravitational lensing. So as you can see here, we have the two orange rays that are paths of light from the source galaxy in the background coming to Earth. So we can actually see light coming from two different directions, and it says here two lensed galaxy images. So we'd actually be able to see the same galaxy twice. So there's only one galaxy, but we'd see two images of that galaxy. As opposed to what we'd normally see where the light would just be a single straight line path to Earth and we just see one image of the galaxy where it should be. And as I said, more light is being directed towards Earth, and so the background galaxy would be magnified. So this was his idea. Einstein at first was skeptical because he thought that this scenario could never occur because you need something extremely massive in order to be able to do the lensing, and his previous experience with lensing had been using the sun as the lens, and the sun isn't anywhere near massive enough to be able to produce these sort of effects. And they talked about this a lot. Einstein eventually did publish these calculations. So down here is some pictures of original letters that were sent from Einstein to Rudi Mandl outlining Einstein's calculations of Rudi's ideas. And these, very interestingly, actually were sold in an auction in 2002. They sold for $50,000. So you can tell they're a very important piece of scientific history. So anyway, Einstein was not completely convinced initially because he thought nothing would be massive enough to be able to produce this lensing effect. But then the Swiss astronomer Fritz Zwicky came along and he discovered, or he didn't discover, but he saw the implication for dark matter in the Coma cluster. So the Coma cluster was a cluster of galaxies, and by looking at how fast the galaxies within the Coma cluster were rotating, Fritz Zwicky calculated that realistically the galaxies within the cluster should all be blown apart because there wasn't enough matter there to produce the gravitational pull to keep the galaxies held together. So his solution to this problem was that there must be some unseen matter there which is holding the galaxy cluster together, which he named dark matter. And with this addition of dark matter, then it would mean that galaxies were heavier than initially thought, and it turns out that this would be the additional amount of mass needed really for this to be a viable option, using galaxies or a galaxy cluster as the lens. So this is what we call strong lensing, when we see two or more images of the same object in the background. And it was about 40 years from this first ideas, from when this idea first came out, before we actually saw any observational evidence of this phenomenon. And this was on the strongly lensed object QSO 0957. So QSO stands for quasi-stellar object, or a quasar as they're more commonly known. So a quasar is essentially the supermassive black hole at the center of a galaxy, which emits jets of radio waves jets of radio waves. So here we can see an image of the quasar. So there's actually two images of the same object. So remember, this is just one object, but because of gravitational lensing, we actually see it twice. And the reason that we know that this is the same object is by looking at the spectra. So on the right-hand side here is the spectra of the two objects. So one of them was labeled A and one is labeled B. So one for each object. And as you can see, the spectra, which is essentially the amount of each wavelength of light that is present when you look at the object, you can see that the spectra are essentially identical. The second piece of evidence that they're exactly the same is that they have identical redshifts. So redshift is essentially a measure of how far away the object is, and within the precision of the measurements, they had exactly the same redshift, so they were exactly the same distance away from us. And the third and final piece of evidence, which probably just concludes everything, is that if you look at the photograph here of the of the lensed object, then you can see that you have the two bright quasars here, but then just above and to the left of the bottom quasar, you can actually see the galaxy, which is acting as the gravitational lens. So this bright dot here, and then the red sort of dust surrounding it is the envelope of that galaxy. So I think that was the nail in the coffin for this one, that they've seen something that could potentially act as a lens in front of the quasar. It must be a gravitationally lensed object. So another really interesting strongly lensed object can be seen here. So here we have a galaxy cluster. So you can see the galaxy cluster with these blobs of reddy yellow galaxies here. So this is the thing which is acting as the gravitational lens. And there is actually a gravitationally lensed galaxy which has been multiply imaged 3 times. So you can see 3 images of this galaxy. One is here, one is here, and one is up here. And what's even more amazing about this is that within this galaxy, which is being lensed, a supernova explosion has gone off. So a supernova explosion is when a star reaches, very massive star reaches the end of its life. It will just explode in a massive burst of energy and produce a very bright supernova. And this supernova was also gravitationally lensed, and you can see here around this single galaxy within the cluster that it was lensed by, you can see 4 images of the supernova. And I think what's even further amazing on top of that is that they predicted that a 5th image of the supernova would appear sometime later in the future at this position SX. So these images of the object don't all appear at the same time, because as the path of light curves, it doesn't necessarily mean that all of the paths are going to be the same length. So because of this, they appear at slightly different times, and they predicted based on what they could see from the gravitational lens. They can model the lens, and they can predict that there was going to be a fifth appearance of this supernova here, and that is exactly what they saw. So here is a picture of the same position on October 30th, 2015, and then a few months later we saw a small dot here, which is the 5th image of the supernova. And of course you can use the same method as before, look at the spectra of the object in order to confirm that it is indeed exactly the same object. Okay, so here is another very dramatic example of gravitational lensing. So this is another galaxy cluster. You can tell from which ones are the cluster galaxies because they are the red, yellow, bright objects in the foreground here, and there are a lot of galaxies that have been lensed by this galaxy cluster. The most notable one is probably this thing here. So this is actually 2 images of the same galaxy. So one image is here, but the second image has been extremely elongated and stretched. So you can just about make out that this sort of banana-shaped feature here, this banana-shaped feature here has about the same colors as this one. And this occurs when the object in the background and the lens are almost perfectly aligned. It's like they're not quite aligned, but they're just off center from the lens. When they are completely aligned, you get something called an Einstein ring. So here is an example of an Einstein ring. So that this is the background galaxy that's been completely warped and distorted all the way around, almost all the way around this lens galaxy here. So this is something that happens when the two are almost perfectly aligned, and we can actually see this using a demonstration of a wine glass and a dot on a piece of paper. So this is one that I did myself. Obviously, if this was the in-person event, we'd have demonstrations of this so you could try it yourself, but if you have a wine glass and a piece of paper at home, then please do try it out. So as you move the wine glass, which is acting as your lens, across the black dot, which is acting as your background galaxy, you will distort the image. And so as you can see here, it's almost on top of the dot, and you can see the one main image here of the dot, which has been completely distorted almost into a curve, just like we've seen for the galaxies. And you can actually start to see a second image here appear on the other side, so just this little black strip here. And then once you move the wine glass completely on top of the black dot, you'll see the dot has been completely warped all the way around the stem of the glass, just like in this Einstein ring example of a galaxy and another galaxy, which is acting as the lens. So we can call this one a Weinstein ring. Okay, so now let's look at a much more extreme example of gravitational lensing. So this is lensing around a black hole. So black holes are the most dense objects that we know that exist in the universe. They're so dense that not even light can escape from them, and as a result we can't directly observe the black hole itself. However, what we can observe is the accretion disk around the black hole. So this is showing a very high resolution simulation of what this would look like if we were able to produce such an image. So an accretion disk is just like how Saturn has rings. Matter is circling the black hole in orbit, and the main difference between this and, say, Saturn's rings is that the material within the accretion disk is extremely hot, because the strength of the gravity of the black hole is causing it to move so fast that it heats up due to friction and releases a load of radiation in the X-ray. So this accretion disk is constantly shooting out X-rays. And then because of the strong gravitational field of the black hole, we can actually see the underside of the accretion disk. So it's almost like I'm showing you my hand here, but you can see the palm of my hand from where the light has been bent round towards you. And you can also see the disk on the far side due to gravitational lensing. So this part of the disk would actually be behind the black hole itself. But due to gravitational lensing, we can actually see that light being bent round and coming towards us. Just for comparison, down here, this is the 2019 Event Horizon Telescope image of the supermassive black hole in the center of the M87 galaxy. You can see some of the same features here as the simulated image, which is really amazing. However, we're clearly quite not yet at the resolution to be able to see all of these features. Okay, and now the final thing I want to talk about before the end of this talk is how we can utilize gravitational lensing to actually detect exoplanets. So an exoplanet is the name given to any planet that orbits a star other than our own. And what I'm showing you here is a graph from the paper that detected the first ever exoplanet by use of gravitational lensing. So what happens here is we have a star in the background and another star which is acting as the lens, and the lens star is slowly moving between us and the background star. And as it does this, more mass is essentially becoming in the way of the light which is coming from the background star to us here on Earth. And so more of the light is becoming lensed. So over time we can see this magnification, so the amount of lensing essentially is increasing up until on the 31st of July 2005 when it was at its maximum. And then as the star moved out again, the amount of lensing would decrease. Apart from about 10 days after the peak, there was a small bump in the magnification. So the conclusion that was drawn was that the actual mass of the thing that was doing the lensing had increased, because a planet that was orbiting the lens star had come into the field of view and essentially increased the mass of the lens, and so therefore it increased the amount of lensing that was happening. And so that's what this small bump here is showing. So that was obviously due to a planet. So that is really, really exciting how we can use this effect to detect planets. Okay, so that's everything I wanted to talk about in this presentation. Thank you very much for listening. I hope you learned something and I hope you found it interesting. And if you do have any questions, then please do come along to the Q&A session after this and we'll be happy to answer them. Thank you.